Hello, welcome back to AE 2220 Dynamics. In this video, we're going to cover impacts of particles. So an impact is a very short duration collision between two objects where the objects exert a very large force on each other. You're probably all familiar with what impacts are, though you've probably never studied the physics of them or the math behind them. So, some examples include pool balls or billiard balls impacting each other or hitting each other. Cars colliding can be modeled as impacts. Asteroids bumping into each other as well can also be modeled with impacts. And there are really two types of impacts that can occur in general. The first are central, and the second type is eccentric. And central impacts occur when the center of mass of each object lie on the lines of impact. You can see on the next page we have these lines of impact. And then eccentric impacts occur when the center of masses do not lie on that line of impact. And so for particles, because we are considering infinitesimal points, we can only have central impacts. We cannot have any eccentric impacts, just given that particles are assumed to have no size. And so for particles, we can only have central impacts, and then there are two types of central impacts. These are direct and oblique. Direct and oblique. So direct impacts occur when the velocity vectors of each particle are aligned with the line of impact. So in this case, we will have a velocity vector RA for particle A, RA dot, and it lies on that line of impact. And the same thing for RB dot, it also lies on that line of impact. And then oblique then are when the velocity vectors do not lie on the lines of impact. So in this case, we can say like RA dot over here points in this direction, while let's say RB dot points in that direction. And they just do not line up on the line of impact. We're going to study direct central impacts, and then we will build on that with oblique impacts, and we'll end up showing that we'll be able to use what we did with central impacts and apply that to oblique impacts. So during the impact, the two particles are going to deform, and at the end of that deformation, they're going to end up with the same velocity. So after that, a period of restitution takes place. This is where the objects are going to try to regain their original shapes, or they're going to end up staying permanently deformed, but there will be some restitution or restoration of shape. So, like I said, at the end of this period, the objects will have either regained their original shape, or they're going to stay permanently deformed. So our objective then is to determine the velocities of the objects after the period restitution, and we're going to represent this with a superscript plus to represent after the impact. We're going to use a superscript minus sign to represent just before the impact. So we're going to write here moment right before the impact, and we're going to have our RA vector here, RA dot, and then this is RA dot minus, and this is RB dot minus. They're pointing along the line of impact shown here, and they're colliding into each other. This is just before impact. Then after the two particles collide, a very short time afterwards, an extremely short time, they're both going to have the same velocity. And this will be at what we'll call the maximum deformation. I didn't draw deformation of these particles, but they will have squished a little bit. And as a result, they will end up moving momentarily with the same velocity. We'll call this R dot. And then after the impact, the two particles may or may not separate. I've drawn them here as being separated. But they're then going to have a new velocity, which we'll say here for A, we'll say is RA dot plus. And for B, we're going to point it in the other direction as well, RB dot plus. Now, these velocity vectors, I draw them pointing in the same direction. They may or they may not be pointing in the same direction. They may point in different directions. It all depends on the velocities of the system and their masses as well. All right, so we're going to now consider the particles as one system, and as a result, then, the linear momentum is going to be conserved. And we can write here that MA RA dot minus, that's a vector, plus MB RB dot minus. This will be equal to MA RA dot plus MB RB dot plus. Move this up just a little bit. And so here, this RA dot plus, that is our unknown, at least in this case, for the derivation of this general theory. That doesn't mean that every problem you'll be given what happened prior. You might be told what happened afterwards, and then you need to go work backwards to determine how each particle is moving prior to this. Now, since the velocities are aligned, we can consider only the scalar form. We don't need to consider the vector form because their velocity vectors are pointing in the same direction. So in this case, we're going to write here MA R dot A plus minus, this is just a scalar, plus MB RB dot minus equal to MA RA dot plus MB RB dot after or plus. And then here, the scalar R dot A plus, this is unknown. And this RB dot plus scalar is unknown as well. So the thing is that we have two unknowns, but only one equation. In order to find another equation, we need to consider the deformation and the restoration that occurs during the impact. So if we consider only particle A during the deformation and the restitution, then we can find that during the deformation there's a force P that acts on the particle, such that we can apply impulse momentum, and we'll get here MA RA dot minus the integral P, this is P dt, equal to MA R dot. So remember that before the restitution, the particles have the same velocity, which we're writing as a scalar R dot here. And then during the restitution, we're going to have, starting off with MA, so we're going to now still have some force. We'll just write it here as R acting on the particle. This is going to be MA for linear momentum, MA R dot minus the integral R dt equal to MA RA dot plus. Okay, so in general, the restitution force as a vector is going to differ from the deformation force, and as a result, we will often find that the integral of R dt is less than the integral of P dt, but in general, it can be less than or equal to that. We can then define the coefficient of restitution, or E as being equal to, E is equal to the fraction of the integral r dt divided by the integral of p dt. Now in general, E is going to be some value between 0 and 1, but there may be cases where the coefficient of restitution is greater than 1. I don't know of any off the top of my head, but it may be possible in some sense. And you could certainly design and create some type of metamaterial that when a collision acts upon it, it violates this condition. But now, actually, the more that I think about this, no, it could happen actually. So in that case, I'll talk a bit more about this in a moment. Well, actually, we'll just do it right now. So whenever you have an impact, and depending on the value of E, there's going to be a change in the energy in the system, particularly the kinetic energy. So in order for E to be greater than 1, there must be some energy added into the system. And so what that implies is that there's some previously stored potential energy that then gets released into kinetic energy. So you could imagine having a spring that is compressed, and then when an impact occurs, it releases that mechanism that's holding the spring. And then as a result, you get a release of the stored potential energy that then causes or increases the kinetic energy of the components that collided. And as a result, you would have then a coefficient of restitution that is greater than 1. Now, that is a very special case, and in general, that's not going to be true. For just two general materials impacting each other without any storage in them, you're going to find that this coefficient of restitution is less than or equal to 1. Okay, so if we go ahead and we solve equations 49 and equation 50, now that we know what this E is, and we substitute in, we can find here that E is equal to R dot minus RA dot plus divided by RA minus dot minus R dot. You can do the same analysis for particle B, and this then leads to E being equal to the fraction R dot B plus minus R dot divided by R dot minus RB dot minus. And then you can manipulate and do some algebra, and then you'll be able to show here that E is equal to RB dot plus minus RA dot plus, all that divided by RA dot minus RB dot minus. Or we can write this in as that RB dot plus minus RA dot plus must be equal to E times the quantity RA dot minus RB dot minus. And this here then becomes our second equation. And now we have two equations and two unknowns, and we can now solve this system. Like I said previously, that E is going to be some value between 0 and 1 generally, and the only way it could be greater than 1 is that if there's some storage mechanism that you're releasing. Conversely, and that would then be a very special case, and that would be true only for that single release of energy. Alternatively, E could potentially be less than, it might potentially be less than 1 if we have the opposite case happening where a impact, well, actually, I don't know. I don't know if it can be less than 0. I was thinking that there might be a case where, the inverse of the spring being released, where the impact then causes the spring to stay compressed. but I'm not certain that that would be less than 0. I'm pretty sure that would just fall between 0 and 1. But, it's worth it, thinking about these kinds of things and exploring them in general. Okay, so we're going to study different cases, starting off with what is known as perfectly plastic impact. And this is where E is equal to 0. And what happens here is that the particles are going to end up sticking together. We can show this just directly from our second relationship, where if E is 0, so if E is equal to 0, we're going to get here that R A dot plus must be equal to R B dot plus. And then as a result, we can see that the particles stick together after impact. And this is what happened with the package and the cart in that example that we saw in the previous lecture. And then from here, what you can go and show then is that MA RA dot minus plus MB RB dot minus is equal to MA, quantity MA plus B, quantity multiplied by a single velocity vector R dot. And that's exactly what happened with the package and the cart. Okay, so that's what we get for perfectly plastic. We'll now take a look at case 2, which is a perfectly elastic impact. This is where E is going to be equal to 1. And in this case, we're going to find here that, I'm just going to scroll up, we're going to have here that R B dot plus minus RA dot plus is going to be equal to R A dot minus RB dot minus. That's our first equation. And then the second one, we're going to get MA RA dot minus plus MB RB dot minus. This will be equal to MA RA dot plus minus or plus MB RB dot plus. You have two equations here, two unknowns, so you're going to have to solve this simultaneously. We're not going to solve it because we're going to just solve it for the next case where E is not equal to 1 or 0. We have to solve this simultaneously. And the reason we're not going to do this is because when we solve for the inelastic impacts, which you can now see what the solution is, you can just plug in E equals 1 and then you'll get the same solution as case 2. So a key thing is to think about what happens with the energy in this system, and is energy conserved with perfectly elastic impacts, or what about perfectly plastic impacts? These are just things to think about. We'll discuss in a moment after we go through case 3 what happens. All right, so for case 3, we're now considering inelastic impacts where E is between 0 and 1. And in this case, we're going to have two equations. We're going to have first here that R B dot plus minus R A dot plus is going to be equal to E times R A dot minus R B dot minus. That's our first equation. Our second equation then is MA R dot A minus plus MB R dot B minus is then equal to MA RA dot plus MB RB dot plus. We're going to have two equations here, and we need to solve these simultaneously. And if you go ahead and you solve them simultaneously, you will end up finding these two expressions for RA dot plus and RB dot plus. You could also solve these simultaneously to find RB dot minus and RA dot minus. Okay, so, is energy conserved during impacts? I want you to take a moment, think about this, and then write out what you think on the page, and then I'll come back in and discuss and answer the question myself. So go ahead and pause the video, and then go through and just answer the question. Okay, welcome back. So the question is energy conserved during impacts? Well, the answer is that energy is only conserved during a perfectly elastic impact. Otherwise, energy is going to be lost unless there's some release of, stored potential energy or something unique going on. So the answer here is that energy, let me scroll up here, energy is only conserved during perfectly elastic impacts. Otherwise, energy is lost during the impact. And just as a reminder, perfectly elastic implies that E is equal to 1. So this energy loss occurs in a change in the kinetic energy. And so what you will find is that the kinetic energy, let's say for a perfectly elastic impact, the kinetic energy before and after the impact is going to be equal. It's going to remain the same. If E is not equal to 1, or we're not considering a perfectly elastic impact, then energy is lost during this impact, and that results due to change in the kinetic energy. So the kinetic energy before the impact will be higher or greater than the kinetic energy after the impact. Okay, we're now going to go on and we're going to consider the case of oblique central impacts, which is about half of a page, and then we will be done with this portion. We'll be done with our discussion of impacts. All right, so an oblique central impact is the case where the velocities are not along the line of impact. So we can come in here, we can draw our velocity, let's say here our A dot, and then we got our B dot. And we're going to say here that RA happens at an angle of theta, and RB dot happens at an angle of phi to that line of impact. Here what we're going to do is we're going to define a normal and tangential coordinate system, and we're going to align here the normal vector with the line of impact, and our tangential vector with, orthogonal to that. So here will be our E hat n vector. So the E hat n is pointing along the impact line of impact, and orthogonal to that will be our E hat t vector. And then we can say that the forces that result from the impact are only going to act in the E hat n direction. They're only going to act in that direction. And what this implies then is that there is no change in the velocity components in the E hat t direction. So the tangential velocity is not going to change. So what can we do then? We can expand our velocities into normal and tangential components. So we'll say here that the vector RA dot minus is going to be equal to some RA dot n minus, that's the normal component, and this is in the E hat n direction, plus some R dot AT minus E hat t, and that's our tangential component. We can do the same thing for the velocities afterwards. So we have R dot A plus equal to RAN dot plus E hat n plus R dot AT plus E hat t. We expand our same thing for particle B. RB dot minus will be equal to a normal component, which we'll write as RBN dot minus E hat n. So that's just the normal component, or the projection of RB dot into the E hat n direction, plus RA dot, this should be RB dot, RBT dot minus E hat t. So that's our tangential component. And then the same thing for RB plus dot equal to RB n dot plus E hat n plus RB dot t E hat t. And then, like we just said, in the tangential direction, momentum is conserved. So we get R dot RAT dot minus must be, or let's say plus, then this must be equal to RAT dot minus. And the same is true for B, so RBT dot plus must be equal to RBT dot minus. And that is how we solve for the tangential components. You can just see that they are conserved, or momentum conserved, so the velocities remain the same in that direction. And now the components that act in the E hat n direction, these behave just like central impacts. And as a result, we're just going to come back up here, and you're going to use the equations 63 and 64 with the normal components. You're going to apply those two equations to solve for what happens in the normal direction. So they, same exact equations. We just, instead of having the velocity vectors directly along the line of impacts, we now have to project them into components and consider normal and tangential components. The momentum is conserved in the tangential direction, so the velocities remain the same, or the speeds remain the same. And in the E hat n direction, we just go and treat that like a central impact. And that covers everything that we wanted to discuss for impulse momentum and impacts theory. In the next series of lectures, we will be going through, first we're going to go through a review before the midterm. And then after that, we're going to switch and study rigid bodies, particularly rigid bodies under plane motion or 2D motion. And then at the end of the semester, we'll go through 3D rigid body motion.